This electron is accelerated across these plates here. And we want to find what the velocity of the electron is right here. It's released from rest right here at the edge of this one, and so it's accelerated towards this positive plate, and we want to find the final velocity. So we can use conservation of energy, and we say that the energy at the beginning plus any work added is equal to the energy at the end, E final. So the energy at the beginning, it doesn't have any velocity, but it does have its rest mass, so we say m naught c squared, m naught times c squared, plus the energy added is the energy due to the potential difference, that's Q delta V. And we're going to let delta V equal to 120 kV. That is 120,000 volts for this problem. And then E final will be equal to, now here's the thing, for the final energy, we could put 1/2 mv squared, certainly it's moving with a velocity, but it also has the energy due to its rest mass. So we remember from the previous tutorial that we can express both of those quite cleanly with this expression. Okay, so solving, if we let this be equal to 120,000 volts, let this be equal to 9.11 times 10 to the minus 31, so we can put some numbers in here. 9.11 times 10 to the minus 31 times c squared. We're going to just leave that as c squared. I use the value of c equals 2.998 times 10 to the 8th meters per second, plus the charge of the electron, 1.602 times 10 to the minus 19. Notice I let it be positive because we just want the magnitude of the charge, because there is in fact velocity added to the particles, so there is energy added to the particles. And then we put 120,000 right here, and then equal to 9.11 times 10 to the minus 31 times c squared divided by square root of 1 minus v over c squared. Okay, so I used a numerical technique to solve for the velocity here, and I achieved 1.759 times 10 to the 8th. So this is 1.759 times 10 to the 8th meter per second, and this is equal to about 59% of the speed of light. Okay? Now, there are a couple of ways that you could have gone about this, and let's take a look at those and see what those answers revealed. You could have let the energy at the beginning be equal to 0 here, and then if you went through the motions and you just let this equal to 1/2 m naught v squared, this is classical physics, right? You would have achieved 0.69 c, which is a little heavy, a little fast. And then here, if you would let this equal to m naught c squared for the rest energy, but then here you replaced m by m naught divided by the square root of 1 minus v over c squared, then you would have achieved 0.94 c. So you would have been real heavy in your velocity. You would have achieved a result much higher than they predicted. And then here, if you just let the work equal to q delta v, and then just replace m with m naught divided by the square root of 1 minus v over c squared, you would achieve 0.61 c, which is quite close to the Einstein explanation, the Einstein hypothesis. Okay. Now, Richard Feynman in the Feynman lectures, he not quite nicely, he put at the beginning of his relativistic discussion, he said, if you just replace the mass, in your classical equations by m naught divided by the square root of 1 minus v over c squared, then everything works out. But if you want to know where it comes from, watch this, and look, that's all that happened here. It's classical physics just with the mass replaced with the new correction factor. And this is actually a decent approximation, isn't it?